Hi, and welcome to Quick Add Maths about solving modulus functions in quadratic form. Let's begin with its fundamental. When sketching any y equals modulus function graph, put up the y equals fx graph without the modulus. Then flip over any portion below the x-axis. The graph on the right shows three examples where function 1 is linear and is represented by the lighter blue. In modulus form, the dotted portion will flip to being the darker blue line. Functions 2 and 3 are quadratic, and their respective modulus form would have the darker blue solid line replace the lighter blue dotted portions. Next, I'd like to talk about number of solutions. In a conventional quadratic equation, you could position a horizontal line to intersect the graph just once, if done at its turning point as represented by the red line. The graph being symmetrical, you could otherwise position a horizontal line that will either intersect it at 2 points, as represented by the yellow line, or not at all, as represented by the green line. From the perspective of the quadratic formula, it has no real roots when b squared minus 4ac is less than 0. This represents the situation when we have a green linear line that does not cut anywhere on the blue graph. And the quadratic formula will have two identical roots when b squared minus 4ac is exactly equal to 0. This represents the situation where you would have a linear red line cutting the blue graph at its turning point. Lastly, the quadratic formula would have two different roots when b squared minus 4ac is larger than 0. This represents the situation where the linear yellow line cuts the blue graph at 2 points. By applying what we have learned to a modulus function in quadratic form, you could see 4 situations. You could position a horizontal line that 1 intersects it at 3 points, inclusive the one at its turning point as represented by the red line. 2 intersects it at 2 points at a position above the red line and at y equals 0 as represented by the two yellow lines. 3 intersects it at 4 points at a position between the red line and the y equals 0 line as represented by the darker blue line. And 4 not at all when y is less than 0 as represented by the green line. It is also to be noted that the number of intersects have a direct relation with the number of solutions. For example, 4 points of intersect implies there being 4 solutions. Let's now go through tutorial question 1. Sketch the given modulus function. As mentioned at the beginning of the video, you will start by expressing y as a function without its modulus. Apply the factorization method in this case to solve for x when y equals 0. This gives us the x value of minus half and 6, which is where the graph would intersect the x-axis. From the midpoint of the given two x's, we will be able to identify the values for the minimum point of the graph. And for completeness, we'll identify the value of y when x equals 0 to locate the position at which the graph cuts the y-axis. From here, we should be able to plot the required U-shaped curve. Also, as mentioned at the beginning of the video, you now need to just flip the portions below the x-axis to complete the required sketch. Tutorial question 2. Sketch the given modulus function. As in tutorial question 1, you would start by working on the function of y without its modulus. Now, if the equation is not easily factorized, you will use the completing the square method to identify its maximum. Next, we will identify where the graph cuts the y-axis and the x-axis. For finding where it cuts the x-axis, in this case, you would have to use the quadratic formula. Again, the final step is to flip the portions below the x-axis to complete the required sketch. For tutorial question 3, I wish to take the modulus function of tutorial question 2, then find the values of a, b, and c before moving to solve for x when the modulus function is equal to 6. To obtain the value of a, one needs to scan where we could position a horizontal line that would cut the blue graph at 4 different points. This would strictly be for when the y values are between 0 and 5. Therefore, a is strictly between 0 and 5. As for the value of b, we now need to scan where we could position a horizontal line that cuts the blue graph at 3 different points. This is possible when we position the horizontal line at the level of y equals 5. This makes the required b as being equal to 5. As for the value of c, we now need to scan for where we could position a horizontal line that will cut the blue graph at 2 different points. This would be strictly when y is above 5, making c being larger than 5. And not forgetting when c equals 0. As for solving for x when the modulus function is equals to 6, we'll use the traditional methods that we have learned. And because the quadratic equation is not easily factorized, we'll use the quadratic formula to get to the values of x. You will find that there will be 2 values of x which concurs with our finding in 3. Now on to tutorial question 4, where we have to find the value of k when the function possesses 2 identical roots, and using the same equation, find the value of k when it possesses no real roots. Knowing that b squared minus 4ac must equal to 0 to possess 2 identical roots, we could position this as an equation and solve for k. And knowing that b squared minus 4ac must be less than 0 for it to have no real roots, we could again work out the equation to solve for k. To our last and final tutorial question for this video, find the value of k for when y equals kx plus 1 is a tangent to the given quadratic equation. I wish to start off to say that when a linear equation is a tangent with a quadratic equation, it also means that they intersect only at a single point. At the point of intersect, the 2 equations will be needing to be equal to one another, and through the rearrangement such that you see a quadratic formula being equal to 0, you now need to only solve for when b squared minus 4ac equals 0 to obtain the required k values. That's all for this segment. If you found this beneficial, do look out for our other tutorials.